You are tuned to the English service of the Yuvavani, transmitting on 217.8 meters, corresponding to 1,377 kilohertz on the medium wave. We are calling listeners from the studios of All India Radio, Hyderabad. Good morning, a big hello and how are things? Hope each and every one of you is doing well and are ready to enjoy yourself this weekend. This Saturday morning, we bring you in our regular broadcast, Know the Institute, a feature on NGRI, National Geophysical Research Institute. It's being presented by V.G. Sindhuja.
The National Geophysical Research Institute is one of the premier research institutes in India. Its origin can be traced back to 1956, when the Central Board of Geophysics, that is the CBG, was formed on the recommendations of the Planning Commission to coordinate and organize research and developmental activities in geophysics. In 1961, the CBG, along with the constituent geophysical and oceanographic wings, was transferred to the CSIR, that is, the Council for Scientific and Industrial Research. The Geophysical Research Wing was named as the National Geophysical Research Institute and started functioning at Hyderabad since October 1961. The then Prime Minister, Srimati Indira Gandhi, laid the foundation stone for NGRI buildings in January 1967 on the 150 acres donated by the government of Andhra Pradesh. It was shifted quarters to its present premises at Uppal in 1970. The NGRI aims at carrying out applied and basic research in the frontier areas of solid earth geophysics, seeking to acquire new information about the structure of the earth. The director of NGRI, Professor Gupta Sarma, gave us an account of the basic areas of research carried on at the NGRI.
We are involved in research programs of basic as well as applied nature in the area of geophysics. The basic studies include the study of the structure, evolution and dynamics of the Earth's crust and its interior, and also the study of the natural fields such as the gravity field, the magnetic field and the electrical fields on the Earth's surface. Study of the structure of the Earth includes the thermal structure, the electrical structure, the density structure, the elastic wave velocity structure, the magnetic property structure as well as possible geological structure at depth. The studies of structure naturally bring the questions about how these structures came to be what they are today. In other words, they seek to find out the geological history of evolution of these structures. In doing so, we try to find what happened at which time in the long geological past in course of the formation of the various rock types, the changes suffered by them, the deformations that they underwent, and such other things as the past history of uplift and subsidence of large rock bodies. The geological processes are still continuing, and this is what brings us to the present dynamics of the Earth. The continents and the oceans as distributed over the globe today are not the same as what they were during the history of evolution of the Earth. The continents have been moving and colliding with each other, and the ocean bottom rocks are being constantly created in certain areas and consumed back into the Earth in some others. Much of the information we are interested in can also be extracted from the physical fields on the Earth's surface, such as the gravity field, the magnetic field, and the electrical fields. We measure such fields and interpret them in terms of possible internal structure. On the applied side, the important areas of research include exploration, instrumentation, geohydrology, and the work on engineering problems. We also study earthquakes, rock bursts, failures in mines, and so on.
What are the different fields where the results of research carried on by NGRI find application?
Many of the geophysical techniques of exploration are applied in order to solve engineering problems such as the determination of the depth to the hard rock basement at the site of large engineering constructions like dams. Actually, exploration geophysics deals with the techniques of finding out what is underground by making measurements only at or near the ground surface. How it works depends on what is the object of research. For example, if one is looking for a magnetic mineral such as iron ore, one can make extremely precise measurements of the variations of the Earth's magnetic field that are caused by the presence of these magnetic material. Electrically conducting targets such as metallic minerals like copper ore and lead ore may be located by making measurements of the electrical conductivity of the ground as seen at the ground surface. The presence of a buried conductor is reflected as some change in the measured conductivity. Similarly, one can induce electric currents inside a hidden conducting target by setting up an alternating magnetic field, and the fields due to the induced currents in the vicinity of the conducting objects show that such conducting objects exist at the locations where these fields are detected. If you are looking for a heavy mineral target such as chromite or barite, you could detect the presence of such targets by making extremely fine observations of the gravity field of the Earth over such areas. The gravity field near such a target would then show its location. One of the most powerful methods of determining underground structure is to sound the Earth by firing a small quantity of explosive and detecting the elastic waves that arrive at the surface after reflection from different underground layers. This can be done by recording the vibrations of the Earth's surface at a large number of points and then interpreting these records in terms of the elastic wave velocity structure of the ground. By using a large quantity of explosive and making records over long distances, it is possible to determine the structure of the Earth to depths of a few tens of kilometers. In fact, much of our current knowledge of the structure of the inside of the Earth down to its core has been based on the study of the vibration of the ground caused by large earthquakes that are detectable at any point on the Earth's surface by using sensitive seismological recorders.
As mentioned by the director, the Institute's activities are now based on a wide range of multidisciplinary capabilities. Its activities include, among others, airborne geophysical surveys, deep seismic sounding studies, that is, earthquake studies, and groundwater exploration. Dr. Atchuta, scientist at NGRI, gave us an account of airborne geophysical surveys.
Ground geophysical surveys for exploration of large areas is time consuming. Sometimes it is also not possible to carry out surveys on ground due to inaccessibility of the areas. During the last 50 years, sensitive geophysical instruments for measuring the magnetic field, electromagnetic field, and the radioactivity of the Earth have been designed by geophysicists, which can be installed in an aeroplane to carry out airborne geophysical surveys. Thus, airborne geophysical surveys have the advantage of collecting geophysical data over a large area in a short time and therefore is cheaper. Surveys also can be carried out over forest-covered areas, deserts, and over water-covered areas such as lakes and seas. Airborne, magnetic, electromagnetic, and radiometric methods are the three methods that are generally used in mineral exploration programs. With a view to develop indigenous capability for these airborne survey methods, the NGRI has been designing and developing airborne magnetic and airborne electromagnetic systems. Proton precision magnetometers and rubidium vapor magnetometers have been designed for magnetic survey, and pulse transient electromagnetic system was designed for electromagnetic surveying. By surveying and preparing the magnetic field map of the area, the nature of the different geological units, rock formations, structures such as faults, shear zones in rocks favorable for mineralization can be identified. The electromagnetic system sends pulses of electromagnetic fields into the ground by passing electrocurrents through a coil of wire fitted as a horizontal loop around the aircraft, and this induces currents in the rocks below the aircraft in flight. These currents decay quickly with time, and the decaying current in the conducting rocks below is picked up by the sensor coil towed behind and below the aircraft. The electromagnetic survey helps in locating electrically conducting ore bodies such as sulfide ores, which are the sources for copper and lead. Aeromagnetic surveys also help in finding details of deep basement structures in a sedimentary basin, which helps in oil exploration. Employing these indigenously developed airborne geophysical instruments, our institute has been carrying out airborne geophysical surveys for the Geological Survey of India, Oil India Limited, and the state governments of Karnataka, Madhya Pradesh, and Uttar Pradesh, and northeastern region of the country, covering more than 260,000 line kilometers to help in the mineral and oil exploration efforts and for basic geological mapping. Starting in the year 1967, with an experimental survey in the Kudramukha region, iron ore belt of Karnataka, the NGRI's airborne survey group, over the years, has successfully contributed to the development of indigenous airborne survey technology.
Dr. C.P. Gupta spoke on groundwater exploration.
Groundwater is an important resource to meet requirements of irrigation, industry, and most important of all, for drinking purposes. Groundwater is the invisible subterranean component of what is known as hydrological cycle. Groundwater is stored underground as water seeps from the surface downwards, mainly as a result of the precipitation, that is rainfall and snowing. During its downward journey, a part of water is evaporated, a part is transpirated, and the remaining is stored in void spaces. If we want to tap this water, a well is drilled and groundwater is withdrawn with the help of a suitable contrivance. This causes lowering of water level in the well, and water from the vicinity flows into it. Now this means that if an area has to have a good potential of groundwater, enough water is needed for percolation, there should be void spaces for its storage, and the formation should have a good transmission property, so that water may be allowed to move downwards and laterally. These features essentially vary considerably from place to place depending upon the climate and geological conditions. Besides large variations of groundwater potential from one region to the other, in hard rock areas which cover about 2/3 of our country, one finds variations in the yields of even closely spaced wells. It is therefore necessary to carry out surface exploration for finding favorable areas of groundwater potential and potential sites for well drilling. The NGRI has been carrying out hydrogeological and geophysical exploration for groundwater, particularly in difficult areas. Under a program on National Drinking Water Mission, NGRI scientists surveyed more than 1,200 villages spread all over the country and found good sources of groundwater for drinking water supply. Besides groundwater exploration, it is very important that the groundwater resources should be managed properly. That would mean that we should not withdraw more groundwater than are replenished annually. It is necessary for this purpose that we should carry out field investigations and the modeling studies in the laboratory. The NGRI has been carrying out these studies for the last few years and have covered a number of typical areas where these modeling studies have been carried out. It is also very important that we should guard against the pollution of groundwater resources. We have been seeing that because of the indiscriminate waste disposal systems in the country, the groundwater resources are getting polluted. It is also important that modeling studies for this purpose should be carried out. The NGRI has also embarked upon these studies.
Director Professor Gupta Sarma spoke to us on earthquake studies.
There are two types of studies that are done with earthquakes. One consists of the studies made on the earthquakes themselves, such as the location of the epicenters and depths of the foci, the mechanics of the focal process, the frequency of occurrence of earthquakes of different sizes in a given area, the study of historical records of earthquakes in the long past, and so on. These studies result in an understanding of the space-time distribution of the occurrence of earthquakes of different magnitudes and helps in assessing the kind of hazard that one may expect from earthquakes in given areas. These studies also allow us to understand exactly why earthquakes occur in certain areas in the earth and they don't occur in some other areas. The other type of study uses the earthquakes as seismic sources only. Using these sources which produce elastic waves that travel far into the earth in all directions, one can find out the internal structure of the earth at different scales, in terms of the various layers at different depths and so on. Seismologists have devised many clever ways of finding details of the internal structure. You may have heard about the X-ray tomography that is used by doctors nowadays to see sections of different parts of our body. One of the common names for this is CAT scan. One can use seismic waves for making some such pictures of the inside of the earth. The name of this is seismic tomography. It is a very interesting new emerging technique.
Besides these, the NGRI is involved in several other activities. Geophysical investigations for examining foundation conditions at dam sites, archaeological sites like Qutub Minar, Taj Mahal, and for many other engineering problems have been undertaken from time to time. NGRI has also been actively participating in the Technology Mission Program of the Government of India for drinking water. Under this program, the Institute has carried out detailed surveys in more than 1,300 villages suffering from the scarcity of drinking water. Further, the NGRI has been monitoring seismicity in the vicinity of dam sites by establishing temporary seismic stations and has provided valuable information about the nature of seismicity induced by large reservoirs. Rock mechanics, magnetoelectric studies, helium studies, preparation of geological maps, geohydrological studies, geochemical studies, geothermics, theoretical geophysics, marine geophysics also form a part of NGRI's activities. To facilitate the several research activities, the Institute is running a seismological observatory and a geomagnetic observatory within the campus. A geomagnetic Earth pulsation observatory at Atchuta near Hyderabad and an equatorial magnetic and micropulsation observatory at Ettayapuram, Tamil Nadu have also been in operation for many years. The Institute also has an advanced mainframe computer system with funding from the Oil Industries Development Board. The Institute's well-equipped laboratories and its excellent library facility enable the smooth functioning of the research activities. To gain a further insight into the working of the Institute, we spoke to the director, Professor Gupta Sarma. In its course of activities, does NGRI interact with any other research institutes?
Yes, we do. We interact with the premier arts and organizations such as the Geological Survey of India, Oil and Natural Gas Commission, and also with the various other research institutes such as the Birbal Science Institute of Paleobotany in Lucknow, Wadia Institute of Himalayan Geology in Dehradun, various universities and government departments such as the Department of Atomic Energy, Department of Space, and so on. We have also had many interactions with institutions outside the country through exchange of visits, invitations to scientists to visit NGRI on long-term basis, and also joint research programs with institutions outside the country. Important joint programs of this type have been with institutions in the Soviet Union, Germany, USA, and Japan. Yes, we have quite a number of programs in which we are engaged at present, but let me tell you only about some of the important ones. One of the important programs is the study of the thickness of the Earth's crust over the Indian subcontinent. This has been measured by using seismic